We're looking at basically, if we put two things into our reaction, what do we think are going to be the products? And you were doing this exactly this concept in your lab. And we were struggling a little bit because we haven't covered exactly how to build reactions yet. So we're doing that today, and I think it's going to help you finish that lab. But we put two things in, and we're going to predict what comes out. Okay? So essentially, this is what we're looking at. We want to predict the outcome of our reactions, and double displacements are the easiest to do that with. And so that's what we're going to really focus on, is building reactions using double displacement reactions. Okay, and we talked about what double displacement or double replacement reactions are. Can anyone tell me what happens in a double displacement reaction? Yeah, they switch, right? The cations and the anions switch places, right? It's when we took our outsides and put them together, and we took our insides and put them together. Do you remember that just a little bit? Maybe, kind of. Okay, so we're just going to basically jump in and try some here. Okay, the thing about building reactions is that you have to build the correct chemical compound first, which means these are always ionic compounds. You got to be able to build a neutral ionic compound first, and then you put it together with another one, and then you balance the equation. So this process of building reactions, it takes a little bit of work. Okay. So first thing we're going to do is we're going to start with this reaction of sodium nitrate reacts with calcium fluoride. Okay, sodium nitrate reacts with calcium fluoride. So you can write it out in word version first if you want, but we're going to build the chemical compounds for these. All right, so sodium nitrate and calcium fluoride. Okay, before we even build the compounds, can you predict what our reaction products would be? Yeah, sodium fluoride and calcium nitrate, right? Before we even put it together, you can kind of predict what those are going to be, okay? So let's go ahead and start working that out. Sodium nitrate, sodium is Na plus 1, nitrate is NO3 minus 1. So do those go together easily? Right? It's a 1-to-1 ratio, right? Both of them have a charge of 1. So it's NaNO3. Okay? It reacts with calcium fluoride. Okay, so calcium is a what charge? Plus 2, good. Remember, it's in the second group. I know this has been a while since we've done our naming and stuff like that, but we got to get back into that. Okay, and fluoride is just F, right? Fluoride is the anion version of fluorine, right? So it just means that it's F by itself, and it has a charge of -1. Okay, so how do we put calcium and fluoride together? We crisscross that. So we drop the charges, we crisscross them down, and we say CaF2. Reactants, now we have to predict our products. And we already kind of predicted what they would be, but it's easier to almost see here, right? Sodium and fluoride are going to go together. Calcium and nitrate are going to go together. The difficult thing, or the thing that you guys wanted to do a lot when you were doing your lab, is that you assumed any subscript it had in the reactant side would be the same subscript it had in the product side, and that's not the case. Okay? So let's look at these individually. Sodium and fluoride are going to go together. So sodium is a +1 and fluoride is a -1, which means it comes together as NaF. Right? It's not NaF2. Right? It has to do with being a neutral compound when it gets to this point. Okay. Our last product would be, we said, calcium and nitrate coming together. What's calcium's charge? +2, and nitrate is NO3 -1. So how many nitrates do we need? We need 2 of them. So it looks like this, Ca parentheses NO3 parentheses 2. Okay, are we familiarizing ourselves a little bit with that again? Yeah, Lauren.
Why did it put F?
Because when it was paired with calcium, calcium's a +2 and fluoride's a -1. So when it's paired with calcium, we have to have 2 of them. But when it's paired with sodium, we only need 1 of them to make it neutral. Okay? So now we go back and balance our reaction. If you built your compounds correctly, your reaction should balance. If you didn't build them correctly, it probably won't balance. Okay? So we've built all of our reaction, we've built all of our compounds. Now we go back and balance our reaction just like we know how to do. Okay? So let's look at balancing our chemical reaction. Something I will point out here is that, see how we have nitrate on both sides? You see how we have an intact nitrate on both sides? You can balance nitrate as a whole. So you don't have to split it up into nitrogen and oxygen. You are welcome to split it up, but you can balance polyatomic ions as a whole if they are shown on both sides. Does that kind of make sense? So if in this case, I would say, okay, I have 1 sodium on each side. That's fine. I have 2 nitrates here, right? Here's my 2, which means I need 2 nitrates on this side. So I add my 2. What does that affect over here? Right? Then I bounce over here. So I have 2 sodiums and 2 fluorides. I already have 2 fluorides here, so I should be good to go. Right? Do you see how when you balance, if you don't want to write out all those, you can kind of just like ping pong back from one side to the other, right? Usually when you change something on the left, it's going to affect something on the right until it doesn't anymore, and that means it's usually balanced. Okay? What questions do we have about building our compounds? So now we're doing a gram-to-gram stoichiometry calculation based on that chemical reaction. So I always start my T-chart with what? Always with what I know, 83.2 grams of NaNO3. So if I'm going to go gram to gram, how many steps do I need in my T-chart? It's 4, right? It's 4 steps. Grams to moles to moles to grams. Okay, grams to moles to grams. So I want to get rid of sodium nitrate, grams of sodium nitrate. And I need to go to what? Good. Moles right here of sodium nitrate. And what does moles always get in this part of my T-chart between moles and grams? Moles always gets the 1. Okay. And then if you don't have your calculator, hopefully everyone grabbed that by now. We need the molar mass of sodium nitrate to go there. Did we? No. Okay, so I've canceled grams of sodium nitrate. I got the molar mass to come out at about 85. Is that what you had? 23 plus 14 plus 48? Yeah? Okay, good. So now if I want to get rid of moles of sodium nitrate, right, you always follow your units. So moles of sodium nitrate, what can I go to? Can I go directly to grams of calcium nitrate? No, I have to go moles next. This is my mole ratio step. So moles of CaNO3, 2. And here is my mole ratio step. So these numbers come directly from our periodic table. So NaNO3 gets a 2. And calcium nitrate, CaNO3, 2, gets a 1. Right? There's no coefficient in front of there, which means it's a 1. So I've canceled grams of sodium nitrate. I've canceled moles of sodium nitrate. Now, if I stopped here, I would be in moles of calcium nitrate, which is not what I want. So I'm going to go moles of CaNO3, 2, and go grams. Sorry, I'm running out of room here. Moles here gets the 1, and molar mass of calcium nitrate, let's see. $164. Okay. So now I've canceled all my units. I multiply across the whole top, divide by the whole bottom. if I combine lithium phosphate and aluminum nitrate, what will my products be? Build a balanced reaction. Okay, so you're going to build and balance this reaction. Do you want to try it on your own, or do you want to do it together still? So lithium phosphate. If you want to do it on your own, that's fine. Go for it. Okay. Lithium phosphate. Lithium is what charge? +1. Phosphate is PO. PO4 -3. Okay, so you might need to brush up on your polyatomic ions. Okay, as we go through this, we'll start using them a lot more, so you'll start remembering them a little bit. But lithium phosphate. So I need to crisscross those charges, which leaves me with Li3PO4. Okay, crisscross those charges down. All right, second reactant is aluminum nitrate. Aluminum is Al + 3. Nitrate's NO3 -1. Okay, once we've got them built now, you should be able to see all the charges. Right? We've got all the charges up here. So now these two go together and these two go together. Right? Outsides and insides. It does not matter which product you write first. Okay, I should make that clear. It doesn't matter the order of your products or the order of your reactants. It does matter which side of the arrow they're on. Okay, so as we look at our products here, lithium and nitrate are a new product, right? That's our cation and our anion. Okay, then we combine aluminum and phosphate. Those are cation and anion. Aluminum has to be written first because it's the positive charge. So in those ionic compounds, it always has to go positive, then negative. Okay? Lithium and nitrate are both 1 charges, +1 and -1, so they went together in a 1-to-1 ratio. Phosphate and aluminum were both 3 charges, so they went together in a 1-to-1 ratio also. So now our job is to balance the reaction. Okay? We've got all of our compounds up here correct. Now we balance the reaction. Okay? So go ahead and do that if you haven't already. Oh. That's it. I think. And I want to change the wording of this question here a little bit. How many moles of aluminum nitrate will it take to produce 311.2 grams of aluminum phosphate? Okay, so there's our balanced reaction. This time we're going to start with what we know, 311.2 grams of AlPO4. And I want to go just to moles of aluminum nitrate. So how many steps is in my T-chart? 3, right? I take one off. I'm going from grams to moles to moles. Okay, so sometimes when we get into those big problems where we go grams to grams, we get into a rhythm and then we don't know how to go back and do the easier problems. Okay, this one is easier than the ones we've done, the last one we just did. But sometimes it's difficult to switch gears there. So I need you to make sure we're recognizing the big picture. We're not just going through the process. Okay, so we get grams of aluminum phosphate canceled. We go to moles of aluminum phosphate. molar mass of aluminum phosphate is, somebody have that for me? Okay, thank you. 122 grams in 1 mole. So I've canceled grams of aluminum phosphate. Now I want to go moles of aluminum phosphate to moles of aluminum nitrate. Okay, so what's this step in my T-chart called? Mole ratio, good. And these numbers come from where? They come directly from our periodic table, and they're both what? They're both 1s, okay? So now you have got to recognize right there that you need to stop, right? I want to end up with moles of aluminum nitrate. What do I have in my T-chart right there? Moles of aluminum nitrate. Okay, so you have to recognize that. Don't just plug everything in because you know how to do 4-step problems, right? Start with what you know and finish with what you're supposed to finish with. Don't do extra work, okay? So as we multiply across the top, divide by the whole bottom, we get 2.6, 2.55. Is that right? Okay. 2.55 moles. Okay. Equals, kind of, yeah? No one? If we say it yields this much, that means it produces. Okay? It makes. So when we talk about percent yield, what we're doing is we're going to basically compare how much was actually made in the reaction and how much it was supposed to make. Okay? So everything we've done so far in our T-charts have been what we consider theoretical yield. Okay? It's what's supposed to happen. So when we put these numbers into our T-chart, we're making calculations based on if the reaction goes all the way to completion. Okay? So if the reaction does exactly what it's supposed to do and uses up exactly what it's supposed to use up, this is the number we get out, right? That's what we've been calculating so far, is what we call theoretical yield. And so theoretical yield, I want you to think about theoretical yield comes from your T-chart. Okay? Theoretical comes from your T-chart. Okay? That means it's what's supposed to happen. The actual yield is what happens if you get into the lab and you perform the experiment and you measure your results. That's your actual yield. Okay? So you don't know an actual yield until you do it in the lab. Okay? So this is your equation that you need to have this down as an equation for percent yield. Actual over theoretical times 100. Okay, and you'll see me write it like this. Actual over theoretical equals percent yield, right? Times 100 is to put it in a percentage, but I assume you guys know that well enough by now. Okay, so actual over theoretical times 100. Hypothetically, should our percent yield ever come out over 100%? Should our percent yield ever be higher than 100%? Probably not, right? It happens because lab things don't always go the way they should. But theoretically, okay, or hypothetically, your percent yield should be 100 or less, right? 100% yield would mean our reaction did exactly what it was supposed to. Every little gram or every little milligram of our of our reactants got used up, and all of the products formed that we're supposed to, right? That's 100% yield. Very rarely does that happen, okay? But that's what we're looking at, okay? So here we go. We're going to start with this reaction. I already balanced it for you. We're going to answer some questions along. So write down what you need to. I'll give you a couple minutes here to get written down what you need to, and then we'll work it together. All right, first of all, can anyone tell me what type of reaction it is? Types of reactions are things like single displacement, double displacement, synthesis, decomposition, combustion.
Is it
Mm-mm.
decomposition?
This is a very specific type of reaction. It has specific reactants and specific products. This is a combustion reaction. Remember, it starts with what we consider a hydrocarbon. So carbon and hydrogen. It reacts with oxygen gas, and it produces carbon dioxide and water. That's that's a ideal combustion reaction, right? Some hydrocarbon plus oxygen yields carbon dioxide and water. That is the definition of a combustion reaction. Okay, so it's combustion. How many grams of water will be formed if 36.5 grams of oxygen are used? Okay, how many grams of water will be formed if 36.5 grams of oxygen are used? So we're doing our stoichiometry to determine how many grams of water can be formed. Right? We're trying to find the theoretical yield of water. Okay, so we start with what we know. Okay, we're starting with oxygen gas. It's important you understand it's oxygen gas, O2, not just O, so that when you find the molar mass, you're using O2, not just O. Okay, any questions about how I got from start to finish there? Did we get it about the same thing in the ballpark? Okay, our molar masses were easy here. So I canceled grams, canceled moles, now canceled moles of water, left with grams of water, and I got about 10.26, 10.27, depending on where you round it, grams of water. Are we on the same page with the T-charts at least? Okay. Okay. Next, it says, what's the percent yield if only 7.95 grams are formed? So 7.95, what is that? Our theoretical or our actual? That's our actual yield. That's saying we went into the lab and we only made 7.95 grams. So if I want to find the percent yield, I take actual, 7.95, over theoretical, which always comes from where? Always comes from the T-chart. So I say 10.26, and I get that to a percentage. Our goal had to be converting this grams of our hydrocarbon to grams of water. So using that T-chart, you went grams of hydrocarbon to moles of that, then moles of water to grams of water. And I think you came out with 17.5 grams of water, roughly, right? That means that is your theoretical yield. Okay, we got that from our T-chart. Our 4 steps gave us 17.7. On the same page with that so far? Okay, all we did was convert 40.8 grams of that to grams of water. Now we look at if it gave a 39% yield. So should your answer be greater than or less than 17? It should be less than. If 17 was what's supposed to happen, 17 is what should have happened. But we know it only produced 39% of what it should have. So your actual yield should be lower than 17. Okay, so as I set that up, I take 0.39 equals actual over theoretical. Okay, and I use 0.39 because it needs to be in a percentage, right? So I have that as a 0.39. My theoretical yield was 17.4. If I need to get A by itself, What do I need to do mathematically? I need to multiply those two things together, and I got about 6.8 grams of water. Okay? Questions? Okay.